portion of all of these questions. So my hope is that questions 10 through 15 kind of build us to be able to effectively address 16. So if we look at question 13, I want to change that 12 to something else. Let's go. Let's make it 18. Okay, so we'll start with 18 there. The whole process here, guys, you've got multiple triangles. Okay, if you were to start trying to find values for x and y, and this is kind of maybe one of the main reasons I've told you this throughout the year, is that you cannot say, I'm going to fixate on that triangle as x and y, and I'm going to find x right away. That's the first thing I'm going to do. Okay? Because if you did that, you would be ultimately looking at that picture right there, and you have essentially a bunch of unknowns, right? There's no way for you to find x. All right? So you have to start in this problem, this picture, somewhere else, okay? And we're going to start here. Like I said, we want to make that 18. So I'm going to start right there, which is going to be, I'm going to refer to these as the white triangle or the yellow triangle. So we start with the white triangle. Now, in the white triangle, I know it's a right triangle, but I'm limited now, okay? My hopes is that it's a special right triangle, and right now there's no measurement there. Okay, what can I do, though? Any ideas on maybe some angle measurements that exist in that white triangle? Okay, we got the 90. What do these arrows here mean to me? Parallel. If I've got parallel lines, I should have those two angles being what kind of angles? Alternate interior. Okay, so opposite interior is not a terrible word either. But so that's 30 degrees, right? Does that make sense to everybody? So now, does that make the white triangle a 30, 60, 90 triangle? And if I'm looking at just the white triangle, and this is something people don't like to do, but there's no avoiding it. Okay, if I look at that white triangle, I have to, I think, until you get real good at this, redraw that picture and deal just with that triangle. And that's my 18, right? Okay, and if that's a 30, 60, 90 triangle, the template of a 30, 60, 90 says that the hypotenuse is always the 2 inside, right? Does that make sense, everybody? Remember doing that? So we get that little equation. So now with that little equation, do you know what n is? What's n going to be in this situation? That's my equation. N is going to be 9, right? And n is always across from the 30-degree angle. So this distance here would be 9. And then across from 60 is 9 radical 3, right? And that, remember, is all from knowing if I got a 30, 60, 90 triangle, this side is 2n, this side is n, and this side is n radical 3. And I just, like we said, we paired that 2n up with that 18. Is that okay? So now what's that do for me? Well, if I go back up to my picture, that makes that distance there 9. And it makes this red distance here 9 radical 3, correct? And now, and again, this might be something that you have to do in redrawing a picture. I'm just going to, I have a little bit of a luxury here of being able to just color things white. Now, does that create a problem or a question much like the first math Excel assignments I gave you? Okay, where it's one 30, 60, 90 triangle and you know one side. So now if I look at that, and I put my 30, 60, 90 template together, this would be n, this would be 2n, and this would be n radical 3, right? If I put these on top of each other, doesn't 2n match up to the n radical 3? So there's my equation. 2n equals n radical 3. Or sorry, 9 radical 3. 9 radical 3, sorry. So 2n equals 9 radical 3. Okay, divide by 2. So n is 9 radical 3 over 2. And that ends up being the side that's opposite 30, because that's what we see in our template down here. Side opposite 30 is n. So for us, that distance right there, 9 radical 3 over 2. A lot of back and forth comparison of the template to the picture to the template. But the idea, if you remember, we drew the template so that it was congruent to the triangle in the question. So we can use that CP-CTC relationship. Now, if that, remember, that's n, how do I go from the n side to, in this case, y, or the n radical 3, right? Does that make sense? So I'm going to take my n side of 9 radical 3 over 2, we'll multiply it by radical 3. So that's going to give me 9. What's radical 3 times radical 3? It's going to be radical 9, which is 3 itself, right? And then it'll be 2 times my 1, so 2. So I get 27 over 2 will be that distance there. 27 over 2. Now you can do this by hand, okay, and maybe we will, but we can check this. Do you have 3 sides of a right triangle right there? You have x, which we said was 9 times square root of 3 all over 2. If we square that, add to it 27 halves, square that, 243. If I take the hypotenuse 9 radical 3 and square that, does that prove to me that I have, for that yellow triangle, the correct legs and the correct hypotenuse? Make sense? I mean, the idea is that if any of those are not right, or not correct, those 243s would not match up. Okay. You can always use the Pythagorean theorem in its kind of simplest form to check these. Now, my hopes are that you realize that the special right triangles are the Pythagorean theorem. Okay, the n, the 2n, the n radical 3, the n radical 2, that stuff is all generated through the Pythagorean theorem, but it's a tool that allows us to actually use the Pythagorean theorem when you have only one known value in your right triangle. Okay, so that's why we're turning to this, because I only knew the 18 to start with, right? If you end up knowing then 2 of the known values, you can find a third using the Pythagorean theorem the way that we're accustomed to, a squared plus b squared equals c squared. Or if I know all 3, I can use that to check. That kind of makes sense? So you always want to start in the triangle that you know the most about. Okay, always start in the triangle that you know the most about. What's another one you guys want to do? That was 13. $16? Okay. So 16 is just kind of give you a quick introduction here to this idea. The way I've got this set up is a little bit contrary to the actual description of that triangle, okay, that set of triangles, but you can do this with any types of triangles that you want. It's called the wheel of Theodorus, okay, sometimes called the Einstein spiral, Pythagorean spiral, root spiral. Starts to look like, so we start with a triangle, and then we keep just kind of building off that triangle as far as we want to go. Okay. Eventually, maybe in some math classes, you'll deal with something in a similar way with logarithms. Okay. You guys ever dealt with the number phi, the golden ratio? Ever heard that before? Okay. You've probably seen pictures of you guys seen this picture before? Okay. The idea of the golden ratio, and there could be, I'm not 100% sure, but could be, that's a logarithmic spiral. There might be logarithmic spiral kind of aspects to this. Basically what phi is if there are certain dimensions on your body, and this is for everybody, like the distance between your pupils, and like the distance between like your, I don't know, like the bottom of your nose to like the line that goes through the middle of your eyes, okay? Like there's certain, and you can look it up, like there's like type in like facial ratios or something like that into Google, and it'll tell you the distances, and it's true for everybody. If you measure your own distances, you'll get that ratio of 1.63 back, which is phi. It's kind of weird. People that are in photography and are interested in photography, a lot of times, is anybody in here in photography, like photography? Okay, you might have heard rules like the rule of thirds or something like that, with like what should be in your four front of your picture, in the middle of your picture, and in the background. If you're able to keep that in ratio of phi, they say it's like it makes like a picture that's appeasing to the eyes. So there's a lot of interesting things mathematically about nature and human nature that we can kind of investigate. And this is one, Wheel of Theodorus one. But what we're saying here is that we're starting with side lengths of 1. That's one. That's a 45, 45, 90 triangle. Then we'll build another triangle on top of it. But that triangle there has legs that were the hypotenuse of the previous triangle, right? Okay. So I'm going to just kind of demonstrate this real quick with these first two. So that was 1. That was 1. This would have become radical 2. Does that make sense? Well, in the homework, the next question says, or I guess the whole question says that every one of these triangles is now a 45, 45, 90. The way I've got this set up in the applet, they're not, but it doesn't matter. If that's radical 2, and this is a 45, 45, 90, isn't that radical 2? So now my hypotenuse would be n times radical 2. So it would be radical 2 times radical 2, which turns into 2. Does that make sense? And then keep working my way around. So this triangle is now going to disappear, or I'm going to neglect it and not think about it. And I'm going to look at that triangle. Well, now that triangle is another 45, 45, 90. So this distance is 2, and this would be 2 radical 2. Does that kind of make sense? And we'll keep playing that game, and I'll let you guys finish that. I don't want to give you the answer away, but you're going to keep playing that game all the way around. So just rehashing real quick, the best thing, in my opinion, to do, and I know people don't always want to do this, but it would be to start the problem only looking at that triangle. Maybe I just draw just that triangle. Once I find O to B, then I am going to look at just that triangle. And I'm going to go around and find all the things about that triangle. And I should know then O to C. So once I know O to C, I'm going to worry just about that triangle, try to find OD. Does that make sense? And once I find OD, I should be able to work and find all 3 segments of that triangle. Okay? So one segment gets you into the next triangle. Okay? Now those are all 45, 45, 90 per the instructions. What other type of triangle could we have used here? 30, 60, 90. 30, 60, 90 is a little bit more difficult, and I saved that one for a quiz, okay, and a test. So this question, and so we'll come back and talk to it again on Wednesday and actually go through the whole thing. Maybe give you an example of a 30, 60, 90. I can change this number. It doesn't have to be a 1. It could be a 2. It could be a 3. It could be whatever. Okay, but the process is the same. Here they've only got 4 triangles. You put 5, you put 6, you put 7, put as many as you want. Okay, we play that game over and over and over again until we get to the final distance. Does that help? Always start in the triangle that you know the most amount about, and that will get you into the one that you know the least amount about. We're cool with that? Keep plugging away at that. If you got any more questions, don't hesitate to send me an email. Somebody in the last class asked if there's anything online that are attached to these in regards to explanations, videos. There may very well be. Okay, just have to do a little bit of digging to see if you can find them, if there are any. I'd like to jump into what our text calls trigonometry, okay, which has really been something that we are already talking about. We've been talking about it. If we break this word down, tri means 3, gon means angle, metry means measurements. We've been talking about triangle measurements pretty much all year long, right? But when we start talking about trigonometry and we start thinking about maybe the course that is attached to trigonometry, okay, it focuses on 3 main ideas, 3 main concepts: sine, cosine, and tangent. Okay. Now we're gonna scratch the surface of trigonometry and using sine, cosine, and tangent. The idea, the thought is that it's its entire course. Okay. I teach an 18-week trigonometry course to juniors and seniors, and by day 1, we've already talked about everything that we're going to talk here for about probably, upwards of a week, maybe a week and a half. Okay. So there are so many more things. Okay. 89 more days essentially worth of information that we can get into in trigonometry. Okay. And that course that I teach is actually an abbreviated course because we could, of the trig book, we only cover about 5 of the maybe 8 or 9 chapters that we could cover. Okay, just what the credentials of roads are. Okay, so 8-3 trigonometry. Okay, there's a lot of stuff here that I'm going to kind of bounce around to for the moment. Okay, the first one here is, what we're going to do is this is going to address the buttons on your calculator: sine, cosine, and tangent. And you've probably used them. Have you used those in algebra? Sine, cosine, and tangent? Do you know what they are? Do you know what they do? Where they come from? Like if I type in sine of 30 on my calculator, does anybody know why it gives back 0.5? So that's my concern. Okay, we can do it. It's not hard. The math that I'm going to show you eventually with the practice problems is not something that is extremely difficult. But I want you to know why it works, where those numbers are coming from, okay? Why when I type in sine of 42, it gives back like a 0.669 number that seems to maybe be irrational, and I think it is, or I know it is. Where does that stuff come from? Why does our calculator know those numbers, and how can we use those numbers to find x's and y's and unknown values in other triangles, okay? And getting to be able to do that, to get to explain that, we have to have some just common agreement on the way we're going to identify parts of a triangle. Okay? So when I say sine, cosine, and tangent, those are called trigonometric ratios. Okay? Short, they call them trig ratios. Ratio means the fraction, right? Okay? It's something divided by a distance divided by a distance. Okay? In this triangle here, we have to be on agreement that if I'm going to focus on an angle, I'm focusing on angle A right there. Okay? I'm going to go through my triangle, and I'm going to name the segments of my triangle based off of that angle. So the location of those sides, or the orientation of those sides, the placement of those sides, is in respect to angle A, or they're based off of angle A. Does that make sense? The way I think about it, I colored it yellow for a purpose. I think about it as kind of a flashlight. If angle A is a flashlight, it's going to shine on the opposite side. So angle A, I go find my opposite side, and I label it opposite. Okay? If we can get that, usually the other ones are pretty easy. Hypotenuse obviously always has to be across from the right angle, correct? So I always identify my opposite, my hypotenuse, and then that leaves me one left over. By default, that one has to be the adjacent. Okay? People sometimes get the adjacent one messed up. So they put it on the hypotenuse, because what's adjacent mean? Like in everyday English, what's adjacent? Beside, okay? Beside or next to. Would the hypotenuse be beside that yellow angle? Right, okay? But in the practice that we go through here, hypotenuse supersedes or overrides the word adjacent, okay? So you'll never label your hypotenuse as the adjacent side, okay? So if I want to look at angle A, I'm going to name my sides per angle A, opposite, adjacent, and hypotenuse like that, okay? However, look at the triangle to the right. It's the exact same triangle, but now I'm going to ask you to focus your attention on angle C. And if I look at angle C now, segment AB is going to be the side that's opposite that. And then segment BC down here at the bottom is my adjacent side. So when I look at that angle, these two things, opposite and adjacent, actually flip positions, okay, from when I looked at angle A. Hypotenuse is obviously still the hypotenuse, right? Okay, that's not going to change. If you can't come to terms with that or don't come to terms with that, you're going to miss a majority of the problems that we work on, okay? We have to be able to describe the opposite, the adjacent, and the hypotenuse, okay? We will never look at angle B, which is the right angle, and try to ask the question, well, what is opposite angle B? Well, hypotenuse is opposite angle B, right? So what do I put there? Do I put opposite or do I put hypotenuse? And then AB and BC are both adjacent to angle B, right? So there's a huge problem with trying to decide what goes where when I look at angle B, okay? So we'll never use what we're going to talk about with the right angles, okay? That's not necessarily the ultimate mathematical reason why. In trigonometry, we explain why you don't ever deal with the right angle with this stuff, but here it's not a concern to us. We just won't ever deal with like the sine or cosine or tangent of 90 degrees, okay? So we get this phrase. You guys heard SOHCAHTOA before? Okay. So SOHCAHTOA is a mnemonic device. Okay. It's a phrase like King Henry died by drinking chocolate milk or Roy G. Biv or something like that to help you remember these three ratios. Okay. Here we're focusing on angle A. So when we write our ratios, okay, SIN, and we say sine. I know it's abbreviated like sen, but if I give you an abbreviation like ETC, what is ETC as an abbreviation? What's that word? Etc., right? So when you're reading in English class and you get to a statement that says ETC, do you say etc. or do you say right? You say etc. You say, when you see an abbreviation, you say the word, right? So SIN is an abbreviation for sine. We're not going to say sen. Does it make sense? Okay. Same thing for cosine, and same thing for tangent. The next part is an angle. So angle A is what we're looking at here. We could have used angle C, but then obviously that would have changed the picture a little bit. But sine of angle A, okay, is the ratio of the opposite side divided by the hypotenuse. Okay, so when I type it on my calculator, let's say sine of 30 degrees. Sine of 30 degrees. Just give me a moment here to draw a quick picture, kind of see if this makes sense to us. If this is the 30 degrees, and I say sine of 30, is this a 30, 60, 90 triangle? Across from N, or across from 30 should be N, and that's my opposite side right now, correct? This is N radical 3, and this is 2N. Well, sine of 30, we just said, was identified as the opposite leg, which is N, divided by the hypotenuse, which is 2N. Well, what does N divided by 2N reduce to? What happens with those N's? They cancel out and leaves you 1/2, right? And if you want to think, okay, well, what if N was 4? Then it'd be 4 over 8. If N was 5, it'd be 5 over 10. Okay, and each one of those reduces to 1/2, right? If you were to take your calculator out right now and type in sine of 30, and we'll have a discussion here in a moment and make sure how your calculator is set up so that this works. If I type in sine of 30, my calculator knows that it should give me back that 0.5. It says that every right triangle that has a 30-degree angle in it, the opposite side divided by the hypotenuse will undoubtedly every single time be 1/2. Okay. Something that we have to pay attention to is we could do all this stuff without a calculator, but you would need like pages and pages and pages of charts. Okay, so maybe if your parents are old enough, you could ask them how did they do sine, cosine, tangent back in high school, and they will tell you that they had pages and pages and pages of charts, and they had to do a process called interpolation, which is like its own little math problem before they could even do the math problem that they're focused on. Okay, to find that 0.5 essentially, because there's a lot of, you can put any number in here instead of 30. So if you put like 31 in there, it's going to give you a really nasty number. Okay, unlike 0.5. And when your parents, or maybe a group of parents that are maybe a little bit older than your parents, maybe a couple years older than your parents, would have had to use charts to do that process to find that number. Essentially, that 0.5 is going to be a scale factor for us. Okay, it's going to be a value that we use to find unknowns. Okay, because all these triangles that we work with are going to be similar. Cosine is the adjacent leg divided by the hypotenuse. Tangent is the opposite divided by the adjacent. Okay, and that's all per the angle that you are focused on. The quick way of remembering this is that we've got these three little key phrases. If we take away, let's kind of demonstrate how it's generated. I mean, it's pretty obvious. If I take away all of the letters here except for the starting letters of these words, we get something like that, right? Okay. And then if we go from the S to the numerator to the denominator, it generates the word SOH. Okay. So that's where we get so. And then ka is adjacent divided by cosine is adjacent divided by hypotenuse. Tangent is opposite over adjacent. Does that kind of make sense? So the first letter tells you the trig ratio, S, C, or T, and then the next two letters tell you the ratio that goes with those. Okay. What we're saying here is that no matter, I'm going to give you an image here real quick, no matter what triangle you deal with, if it has, let's say, for instance, a 30-degree angle, when you take the opposite side divided by the hypotenuse, you will always get 1/2. So what I'm showing you here, you got a right triangle, correct? I think I've used and demonstrated GeoGebra enough that we can all agree that it finds distances for us, right? So this distance BC and this distance BA, if I put them in here, if I ask you to show it, okay, it's got the capacity to find those lengths using the distance formula, because these are ordered pairs, right? So you can use the distance formula that we know from chapter 1 to find these two distances. Looking at this triangle, when I divide them, it gives me 0.5, right? Now, as I change the size of the triangle, you see the numerator and denominator, the divisor and the dividend, they change, right? But did the quotient change? No. So no matter what, if I've got a triangle that is 30 degrees, it's a right triangle with a 30-degree angle, the opposite side of that 30 degrees divided by the hypotenuse will always be 1/2. Okay? If we show the adjacent by the hypotenuse, now think about a 30, 60, 90 real quick. My adjacent side would be this side right here. And that's my n radical 3 side, right? My hypotenuse would be that, which is our 2n side. If I take adjacent, n radical 3, divided by 2n, what's going to happen with those n's? Cancel out. And you're left with radical 3 over 2. If I were to ask Desmos, what the square root of radical 3, I guess square root of 3, over 2 is 0.866. Do some rounding here. Is that 0.86603? Well, Desmos going 0.025, so it's rounded up that one. Okay. Does that kind of make sense what's going on here? Okay. No matter what I do, if a 30-degree angle, the cosine, or the adjacent divided by the hypotenuse, obviously the distance has changed, but the ratio is always the same. Okay. And I want to talk about why that's the case. And we already know why the case is, but we should hopefully draw some links to it. So let's draw a triangle here real quick. This all comes from section 7.2. If you remember what 7.2 was about, the AA similarity statements. All right, so I'm going to say that I've got this triangle here. We'll just call it A, B, C. Let's focus on angle A here. Okay, so this would be the opposite of A. This would be the adjacent, and this would be my hypotenuse, right? Okay. I'm going to, just to make things a little bit easier, I'm going to call this lowercase a, lowercase b, lowercase c. That's usually the way when we get into trig that we start dealing with naming side lengths of triangles. Okay. So if I do that, would you guys agree, so cut and paste basically, that these two triangles are congruent, right? All right. Well, what I'm going to do is just stretch that one. Okay. Would we agree now that they're no longer congruent, but do they both still have that angle A up top? Do they both still have my right angle down here at the bottom left? And they both have angle C, right? Okay. So what we've got going on here is two triangles that are similar by angle. Okay. I'm just going to put prime notation on these things. And I'll even do it for the lowercase letters. But those are similar triangles. So now, if you remember what we learned about triangles that were similar, didn't we say back in chapter 7 that this segment here, if these two triangles are similar, should compare to that one? That make sense? So I'm going to say that C compares to C prime, just using the lowercase notation instead of A, B, and A prime, B prime. It doesn't matter, though. You can use either one. Didn't we say that this distance here should match to that distance or compare to that one? So I'm going to say A to A prime. And then the hypotenuses should also be similar. Okay? Those were the three ratios that we said were a result of the triangles being similar. Okay? From angle. Now, I just want to look at, so let's deal with, let's just look at these two. And the reason I look at those two is because A is the opposite side and B is the hypotenuse. Okay, so if I look at A over A prime equals B over B prime, we know that that's a true proportion. Have we talked in the past with proportions that if you take those two things right there, anybody remember what those two positions are called? Those are the means. Did we talk that we're allowed to exchange the means? We're allowed to replace them with one another? And when we replace them with one another, let's look at what it does. it's going to give me A over B equals A prime over B prime. And that's a unique thing. What that is saying is that the adjacent, or not the adjacent, sorry, A is the opposite. The opposite side of the small triangle divided by the hypotenuse of the small triangle should equal the opposite side. So A prime now is the opposite side over here of the big triangle. I'll say opposite of the big triangle divided by the hypotenuse of the big triangle. Does that make sense? So it's saying if you were to take the opposite side divided by the hypotenuse of this triangle right here, it is the same exact thing. That's what the equal sign says, right? It is the exact same thing, the exact same quotient that you get if you take the opposite side of the big triangle divided by the hypotenuse of the big triangle. And because that relationship exists, we call that the sine function. So we say the sine of A is opposite divided by the hypotenuse. And every triangle, no matter how many triangles I make that all have a right angle and angle A in them, if I label opposite and hypotenuse correctly, whatever the side lengths are, when I divide them, they're going to divide to the exact same ratio. Does that make sense? And that's what your calculator is programmed to know. Okay? When I type in on my calculator, I'm just going to use Desmos for the moment. When I type in sine of 30, it knows that the opposite side divided by the hypotenuse of any right triangle that has a 30-degree angle in it is always 1 to 2. It's always n over 2n. Does that make sense? Okay. Think about this. Let's go. If I were to draw, so tangent of an angle is equal to opposite over adjacent. Okay, that's the ratio. If I look at, let's say I put in a 45, 45, 90 triangle, and I want to focus on that 45-degree angle right there. Would you guys agree that that's opposite and that's adjacent, that 45 degrees? Give me a number for opposite. 4. So what's the adjacent have to be if it's a 45, 45, 90? Has to be 4, right? If you take 4 and divide it by 4, what do you get? If you do that right there, what do you get? 1. So the question is that the calculator knows then, if I go tangent of 45, it knows it should be taking a segment and dividing it essentially by itself and getting that 1. That's what 4 divided by 4 is, right? Okay. So what is going on? Well, what happens if I get like a 44-degree angle? Okay, pretty close to 45, but now the quotient is not 1 anymore because one of the sides is just a little bit bigger than 4 and the other one's just a little bit smaller than 4. Does that make sense? Okay, and then that quotient then will deviate from 1 just a little bit. Okay, so our calculators are programmed with this kind of built into them, and at some point, if we have time and we talk about enough of this stuff, I'll explain how your calculator is actually doing this because it's not using charts or tables or anything like that. But one thing I want us to pay attention to and understand though here, and this will get you in a world of hurt if you don't pay attention to this. Your calculator has 2 ways of talking about an angle measurement. Okay? Think about this. If I was going from Lima to Cleveland, could I say, and I don't know if this is a real number, but could I say the distance is 273 kilometers? Is that okay to talk about distance that way? 273 kilometers. There's only a few of us that probably understand or feel or recognize what a kilometer is, right? Okay, if you run cross country, you probably know what a kilometer is, right? You run track, you probably know what a kilometer feels like, right? If I say 273 kilometers, that distance is really kind of bizarre to us, kind of abstract. But if I say the distance from Lima to Cleveland is 203 miles, do we understand that a little bit better? Does that make more sense? Does miles make more sense to us than kilometers does? Okay, so degrees and radians are the same thing, okay, for angles. There's 2 ways to describe an angle. You have 2 measurements, two labels, two units. One of them is degrees, the other one's radians. You've probably never heard of a radian before, correct? You've heard of degrees before, right? So we want to be working in degrees because that unit makes most sense to us. So to do that, there should be a mode key on your calculator. Okay, I'll go through several different calculators here showing you how to do this. If I have a TI 8384, I'm going to hit mode, and I'm going to go down to the fourth line here, go over to degree, and hit enter. Okay, then I'll second quit and get out of there, and now if I hit sign of, say, 30, it should give me back 0.5. Okay, if I typed in sign of 30 and it was in radians, I'll just kind of show you the difference here. If I was in radians, sine of 30 is not 0.5. Okay, so we're going to use this 0.5 as a scale factor. Okay, and we'll use it as sine 30 in our problems. When you type in our calculator that way, you have to make sure you're in the right mode. Okay, your handhelds that are not the TI 8384, they only have one or two lines in a view screen. There should be a DRG button. DRG right next to the second key probably. Okay, and that will toggle where it says, like in small print on your screen somewhere, usually next to the 0, there'll be like a DEG, RAD, GRAD or something like that. If you hit that button enough, it will toggle to DEG, and that's the mode you want to be in. Okay. One of those calculators, I think you have to hit DRG and then hit your directional key to highlight which one you want. One thing to pay attention, if you borrow a calculator for someone, especially if you borrow one from maybe an older person, or maybe you use one of mine in my class. I teach trig first and second period. They use my calculators. We work with solely radians in that class. So they change my calculators all the time to radians, and they do all their work, and then they just go throw them up on my desk, right? Well, when you grab it, then if you're the first person to grab that calculator, it's in radians. If you don't pay attention to that, all the questions that you do will be wrong. Does that make sense? 5 years ago, the end of course exam had a built-in calculator, Desmos, built-in calculator. It was default on every question to refresh itself and go to radians. About 99% of the people did not know that. Okay? Things to pay attention to with your technology. You got to know how it works and what it's doing. Always check what mode you're in. We want to be in degrees right now. Okay? Tomorrow, we'll pick up from there. Or I guess, Wednesday? We'll pick up from there. Make sure that you get that worksheet typed in before Wednesday morning. No new homework this evening.